All right, so moving on, let's talk about energy and reactions. So we've seen two types of energy: kinetic energy and potential energy. Kinetic energy has to do with things moving around. So as things move around, they have a certain amount of energy, and that's called kinetic energy. If they're not moving, they don't have kinetic energy. Okay, and then we have potential energy. Potential energy is related to either the position or the composition of the matter that we're talking about. In this case, we're talking about molecules. So the potential energy we're going to be dealing with is the composition of these molecules, and the potential energy that's associated with the structure and the bonding in the molecule. Okay, and when we're dealing with reactions, we're going to be dealing with both the reactants and the products and the potential energies associated with all of them. Right, so the bonds in the molecules determine the potential energy that's the molecule has. So as we break bonds and reform bonds, that energy, we're going to see that energy appear either as excess energy or as a certain amount of energy that we're going to need to get from products to reactants. Okay, so thermodynamics, which we're not going to talk too much about here, but thermodynamics is ultimately the study of energy and reactions. Chemical thermodynamics is. And the first law of thermodynamics states that we can't create or destroy we can't create or destroy energy. That means that if I have reactants that are a higher potential energy than the products, that there's some energy difference, and that energy has to go somewhere. Or if it's the other way, my reactants are lower energy than my products, then I need to put a certain amount of energy into the system to actually get the products to form. So we're going to see that most of the time that the potential energy of the reactants and the products is not the same. So there's going to be this either release of energy or absorption of energy during the reaction process. So we have this value called heat of reaction. It's delta H with an RxN subscript. The RxN stands for reaction. Delta H is known as the heat of the reaction. It's called enthalpy, which we're not going to talk about here, but if I do say enthalpy, that's what this is. That thing in front of that triangle is a delta. It's a capital Greek letter delta, and that means change. When you see a delta, it means change in whatever is listed next. So delta H reaction is the change in the heat of the reaction. So it's the amount of heat that's either added to the system to get from reactions to products or emitted by the system if the reactants have higher energy than the products. So delta H, the heat of the reaction, is calculated by the potential energy of the products minus the potential energy of the reactants. Again, if that difference, if the reactants are higher energy than the products, then delta H is negative, and energy is released. If products are higher potential energy than the reactants, then we have to put energy into the reaction to get to the products. So there are different ways of estimating what the heat of the reaction will be for a specific reaction. One of the ways is through bond energy. So each bond that forms has a certain amount of energy. That's the potential energy we're talking about. So as we break bonds, in order to break bonds, we have to put a certain amount of energy in. Okay, so breaking bonds doesn't produce energy. Forming bonds produces energy. Breaking bonds requires energy. So if I want to break a carbon-hydrogen bond, on average, I would need 414 kilojoules of energy per mole of bonds I have. Remember, a mole is 6.626 times 10 to the 24. We're going to do a lot of things per mole because of the number of molecules that are undergoing reactions. Okay. So if I want to estimate the overall delta H of a reaction, I can figure out the total amount of energy required to break bonds, and then subtract off the amount of energy that's released when we form bonds. So in the table, we can see the different type of bonds: the carbon-hydrogen single bond, oxygen-hydrogen single bond, carbon-carbon single bond, carbon-carbon double bond, and so on, and the bond energy. So if I have the bond and I want to break it, that's the amount of energy I need to put in to break it. Okay. If I have the carbon and the hydrogen, for example, and I want to form a CH bond, that's the amount of energy that's released when that bond is formed. Right. So you can see how these vary. You can see that double bonds require more energy to break than single bonds because double bonds are stronger. And these are averages. So if you find a CH bond in a certain molecule and then look at the CH bond in another molecule, they might have slightly different bond energies. Or if I've got 4 CH bonds in one molecule, each of those energies might be slightly different. So these aren't exact, they're kind of average. So we can get an estimation of delta H, the heat of the reaction, based on bond energies.